Well, hello, everyone, and welcome to the CQC2T seminar given by Giacomo Pantaleoni. He's a student of mine from at RMIT, and the session is being recorded, just FYI. And so Giacomo has had an interesting trajectory in his PhD. So he did his undergraduate training in Italy, and was it at Padova, Giacomo?
Yep.
I forget. Yeah, at Padova. And undergraduate and master's degree, same?
Yeah.
Yeah. And so you did your master's in particle physics, though, which I thought was quite
That's
awesome.
correct.
And then he's done at RMIT, he's done a partly experimental and partly theoretical PhD. So Giacomo has made rapid progress with my group in the last 2 years, 2.5 years. He's only had 2.5, even though he's coming up to the end. With me after working for a year with in Alberto's group and getting some experience in the lab. So today he'll be talking about work that was recently published in PRL with myself and Ben, who's a co-supervisor. And yeah, so Giacomo, take it away.
Thanks. Yeah, thanks everybody for logging in, I guess. And as Nick said, today I'm going to be talking about mostly about the content of a paper, of a specific paper, Modular Bosonic Subsystem codes, but also I'm going to give you an idea of what else I've been working on, which is basically an extension on top of this work that goes more in depth. So let's begin. I'd like to begin this talk by dividing up quantum physics in two separate groups. Depending on how and where you study quantum theory, you may be more familiar with one or the other. What I'm talking about is that we can have a quantum system that has a finite number of eigenstates. And in particular, because we are talking about quantum computing and because we're doing quantum information theory, the discrete variable physical system is going to be the two-level system. And states living in this type of system are usually called qubits. And they can be represented on the Bloch sphere. You can see a picture here of the Bloch sphere. And you can see that a state in this Bloch sphere can be parameterized by a pure state in the Bloch sphere can be parameterized by these theta and phi parameters. Now, quantum computing is, when we do quantum computing, we want to do algorithms. We want to implement these algorithms that very smart people have written. For example, here I have Shor's algorithm. It doesn't really matter. It's just an example. But we have an input. We have a bunch of unitary operations that we do on this input, and then we have an output. With this output, then we carry on with the larger algorithm. But the most important part that I want to point at here is the input and computation here. These computations are qubit computations. So they happen in a Hilbert space that it's a tensor product of a bunch of two-dimensional Hilbert states. That is where a bunch of qubits live. Now, in contrast to qubits, when our quantum system is in a superposition of an infinity of eigenstates instead, what we're talking about, we enter in the realm of continuous variable quantum mechanics. Now, we've all to different extents seen the harmonic oscillator. We're given a Hamiltonian in terms of these Q and P operators, sometimes called the momentum and position or the quadratures of the harmonic oscillator. What we do is we diagonalize this Hamiltonian, and what we find is that we have an infinite number of eigenfunctions for this Hamiltonian. That is, we have an infinity of eigenstates, and our underlying Hilbert space is going to be an infinite Hilbert space. Now, on the left, you can see a picture of the first few self-energies of this harmonic oscillator. it doesn't really matter for now. What you really want to keep in mind is that it's this dichotomy between the continuous variable, i.e. harmonic oscillator, infinite Hilbert spaces, and qubits, that is two-level systems. Two-level systems. Now, why do we care about the harmonic oscillator? Well, we care because it's ubiquitous, it's experimentally easy to realize and control, it's scalable, it's room temperature. It has a lot of nice properties that physicists like and are very well acquainted with. Now, how do we use it if we want to do quantum computing? Quantum computing lives in finite dimensional Hilbert states. We have an infinite dimensional Hilbert state here. So how do we use it? Well, the answer is we use encoded continuous variable quantum computing. That is bosonic codes. What's a bosonic code? I'm just gonna explain what it is in a nutshell. So suppose we have this qubit state on the left, A0 plus B1, where A and B are the amplitudes of our qubit. What we do is we pick two wave functions, psi naught and psi 1, and we say that we realize our qubits by considering a superposition of two wave functions. Now, what are these wave functions? That depends on the specific bosonic codes. What are the properties of these wave functions? That also depends on the bosonic code that we pick. Here, I won't give you a review of bosonic codes. I'm just going to pick one that we like particularly in our group, and this group is this bosonic code is the Goddess Monkey Type Pascal code. Now, why do we like this code? Because it's resilient against noise, actually against it's very robust against a noise that it was not designed against. So that's why it's so interesting. And another very interesting thing about this code is that the Clifford group, which we need for discrete variable quantum computing, is implemented very simply. We just do Gaussian operations, which in the optics community are considered easier than are considered easy operations to realize on a continuous variable state. So here's the qubit that we use to encode a zero state. It's a Dirac delta comb, where each of the spike in the comb is spaced by 2 root pi. On the right-hand side, we have a one state, the state that we use, the wave function that we use to encode the one qubit, the one state. And it's essentially the same as the zero state, but shifted by root pi. And if we want to look, and if we want to have a superposition, a qubit in general, that is a superposition of these two qubits, we can just look at the bottom and we just take the two wave functions and take a superposition of those. Now, I would also like to point out that when I say that the GKP code is easy to operate, when we say that Gaussian operations are easy to perform on it, I'm kind of not telling you that realizing GKP states is actually kind of hard. So that's where the trade-off is. It's easy to use, it's resilient, but these states are pretty hard to make in a lab. Now, suppose we want to know what the qubit state is. What do we do to learn this information? Well, what we do is we perform a homodyne quadrature measurement. In particular, we measure the position quadrature. Therefore, if if our measurement falls, for example, here around the 0, or around 2 root pi, or in an even bin, then we have a 0 qubit. That means that our qubit has collapsed to a 0, to the 0 eigenstate. Conversely, if we measure the our quadrature in a odd multiple of root pi, then what we have is a 1 state. We have collapsed our state to the qubit state 1. So do we need this V? Do we need this deviation from the original position of the grid? No, that is redundant information. However, if these V, so V is a drift essentially. So think of the state as something that we have made in the lab and it's there waiting to be used. Our error model is that our states drift by a little bit over time. And as we can see, as long as it drifts but stays in between the original bin, then we don't have a bit flip. We don't have an error because we never care about this V here. However, if it drifts too much, that means that it goes on the adjacent bin and a bit flip is performed. So this consideration tells us pretty much how to perform error correction, because since we don't care about this shift as long as it's not too large, we can simply measure the quadrature mod root pi. That way we only learn by how much the state has shifted rather than which bin it's in, the state is in, the quadrature falls in, sorry. So I'm going to talk a bit more about this later. But for now, I also want to address the elephant in the room, which is these states have two very bad infinities. I guess they're not very bad. They're two different infinities. So it's not a physical state. One infinity is that it's an infinite sum of something. The second infinity is that that something is actually a Dirac delta function, which is, it has infinitesimal peak width. It's a non-physical function. This is how we make a GKP state physical. In this example, we can see a 0 state. Could be, but we could also do the same for 1 state, for a superposition of states. What we do technically is we first convolve our delta train with a Gaussian function, which is just a fancy way to say that we take the deltas and make them into Gaussian functions. And after that, we multiply by an envelope function and with a Gaussian shape. That is, we kill the we kill our wave function for high values of the quadrature, therefore making it finite. So this now is a valid wave function for a this is a valid physical wave function that we can actually use, and we can think of our schemes in terms of these. Now, obviously, we introduce problems when we do this, and the problem is that if you can look at this, the middle peak, we can see that this 0 state is actually kind of leaking a little bit on the neighboring bin. What does that mean? This means that we have a probability of measuring a state that's supposed to represent a 0 as a 1. And that's a problem, because that means that what we intend to use as our computational basis states, they're actually not orthogonal. there's a second problem. The second problem is that if we shift a Dirac delta comb by 2 root pi, we get the same thing. Therefore, we have a well-defined stabilizer for our code, which is translations by 2 root pi. This is no longer true now, because if we shift by 2 root pi, we get a different wave function. So we lose this error correcting property, if you will. Now, does this mean that everything is horrible and it's ruined and we can't use it? Obviously not. We just have to be careful and take care of this kind of thing, and consider what it actually means for the logical component of a wave function to be in this sort of approximate limbo, let's say. And yeah, at this point, one may have many questions and problems that they may want to address with this whole thing, GKP approximate code words. I focus on one whose solution, I believe, answers many of the questions that one may have. But that's not, I'm not saying all the problems of the world are solved. Let's read the slide. Let's see what's in this slide, which is a bit of the common thread of the whole talk. Now, the problem is that there is no explicit procedure to define and extract qubits from any wave function. And by any, I mean any wave function. You give me a random wave function, and I tell you what the qubit state is. And if we want to solve this problem, we also want the solution to bring a couple desirable features. Now, I literally write two, but there's actually more than these. These are the two most important, in my opinion. Now, we want to be able to convert or translate continuous variable schemes into the qubit counterpart. So you take a continuous variable computational scheme as a whole, and then this mystery procedure is going to spit out the qubit version of that. That would be nice. That's a feature that I like my solution to have anyway. And another desirable feature is that we want to be able to use the full quantum information toolset defined over quantum computing. That is, we want to be able to take fidelities, we want to be able to represent the logical information in block sphere. And below, you can see a schematic picture of what the problem is, essentially. We have psi, we have some wave function in the Hilbert space of the harmonic oscillator. What state, what qubit is it hiding, so to speak? Which qubit, what does that represent in the block sphere? That's a problem. And because this is so important, this is just a reminder slide. Logical information and extra information in the GKP code. Now, position quadrature carries information as follows. Even bins are associated to the 0 state, the logical 0 state. Odd bins are the 1 state, and small position shifts do not induce logical bit flips. Just remind this, and you're good to go. The solution turns out to be, there is a framework that makes the solution of the problem that I defined earlier super easy. And this framework is modular variables. Zach and Aharonov discussed these, introduced and discussed these in 68 and 69. And I'm briefly gonna reintroduce them again with my notation. And the idea essentially is this. We have a real number, and we just write it as a quotient plus remainder. So an integer multiplied by root pi. Why am I multiplying by root pi? Because of GKP compatibility. So don't think too much of that. So we have our number, and we just write it as integer quotient plus remainder. This m here is an integer, and this u here is a continuous variable that lives inside the bin, essentially, the bins that you've seen when I was plotting the GKP wave functions. A modular variable is actually an operator. That means that it's the operator version of what I just said, which also means that we just essentially operatorize these relationships above. So our quadrature, our position quadrature operator becomes this modular variable plus the integer variable. Now the spectrum of the integer variable is the integer numbers, and the spectrum of the modular variable is the bin size. So it's an interval with size that starts at minus root 2 pi, root pi on 2, and to root pi on 2. Now, we have two operators which commute. Therefore, they define a basis of simultaneous eigenstates. Therefore, we have this mu basis, which is the basis defined by the simultaneous eigenvalues of these m and u operators. Now, what's the big idea? The big idea essentially is we do this twice. Why do we do this twice? Well, the main idea is that now we have this m operator, which is an integer. How do we take any integer and we map and we build a qubit? That's easy. We simply take its parity. So our decomposition is going to look like this. We take our quadrature, root pi m plus u. We take our m, which is an integer, and we simply rewrite it as its parity, that is 0 or 1, plus twice an integer. And that's pretty much, and that's the blueprint for our change of basis. Now we start with position eigenvalue. We get this mu version of the position eigenvalue by simply using modular variables. We take that and we obtain this 3 quantum number decomposition or basis. That is, we have one label that's either 0 or 1. We have one label that's integer, and we have one label that's inside the interval. We also give a name to these subsystems. L is the logical subsystem because there's only two eigenstates. There's the 0 state, there's a virtual 0 state, the virtual 1 state, and they're essentially a qubit, a virtual qubit. And the leftover, which we don't care about because it does not contain logical information, we name the gauge mode. This name is inspired, or rather, we're just using the same terminology of usual normal subsystem. I shouldn't say normal. I should say traditional subsystem codes. Wherein the gauge mode, wherein the systems are divided in logical and gauge mode. Now, in case this is all a bit obscure to you, I'm going to show you an example on a real world, not so much, but on a wave function, on something that tries to represent a state. Consider this sine or cosine. What I've done is I've already split it up in all the bins, and I've labeled the bins. So as you can see, this would be the mu representation that I've already introduced. So if we wanna describe a point of this wave function, we would have to give both the bin number and the u variable, the modular variable. Now, what our decomposition does is essentially it separates the odd m's and the even m's. Then it relabels pairs of bins rather than the single bin. And it associates the top-bottom information with a qubit, essentially. These are two separate subsystems. The qubit subsystem is what we have here on the right, tensor wave function, and on the left, we have the gauge subsystem. Now, if in this particular case, we realize that our wave function on the top is simply the wave function on the bottom with a pi phase, then in this particular case, not every time, but in this particular example, we can write it this way. Therefore, we have a gauge wave function that kind of factors minus state, a state that's proportional to the minus. Why is this cool? Well, this is cool because it tells us because if we look at the logical subsystem here, the minus L, we now have extracted a qubit from a seemingly unencoded wave function that is a sine. Now, we can do this for more useful states. For example, we can use this for the plus GKP state, and the result is shouldn't surprise anyone. That is, if we take the wave function for a GKP plus state, we have that the logical state that's hidden within the whole mode is a plus state. The gauge wave function is another copy of the very same plus GKP state, but what we really care about usually is the logical information. But we also have other states that encode the very same information. For example, if we take a zero momentum eigenstate, we can decompose it, look at the logical information, and what we find out is that it also contains a plus state, which is cool. We have the same logical qubit using completely different wave functions, and therefore they have different gauge modes. Up until now, I've been describing a very idealistic world where states go up to infinity, etc., etc. But all this stuff generalizes to mixed qubit situations once we realize that we have a map that is the gauge trace that just takes any CV state, any continuous variable state, and gives us a mixed, in general, qubit. Now, I'm just going to read this because it's very important realizations, I think. Number one, ideal GKP states are separable states with respect to the decomposition. Number two, for approximate code words, the logical and gauge subsystems are entangled. And number three is there is a natural map from the full Hilbert space, that is the harmonic oscillator, to the Bloch sphere, i.e. tracing over the gauge subsystem. And this is essentially how we take any wave function and get a qubit out of it. The rest of the talk is pretty much me showing you how we can use this formalism, how we can take CV schemes or just simple CV code words and make more sense of them with this decomposition. The very first example that I've ever looked at is, let's fix.
Excuse me.
Yep.
This seems to be just one of the ways that you can like do Cantor's arguments of equivalence of different countably infinite sets as extracting a qubit. Are there any, like, aren't there many other natural ways that you could do the same thing? Have you looked at whether those are equivalent or not, or things like that?
Well, the easiest equivalent way to do this would be to just do the very same decomposition with the momentum quadrature. This is almost trivial. I believe there's other ways to do this. I haven't looked at them, and in fact, if you, I'd like your thoughts on that. Essentially, don't be afraid.
Can I interrupt for just 1 second?
Yeah.
Sorry, Giacomo. I think that the questions during the talk should be entered in the chat. I believe everyone has option to chat, just so that we maintain time. And Giacomo, I think it'd be good to finish in about 15 minutes so that we have ample time to answer
15?
good questions like that. Yeah, so finish by about 10 to 3 with the actual content, and then we can answer these questions.
Cool.
But yeah, if you have further questions, please put them in the chat. I think people should have access to that. If you don't, please message me in the chat. That should be possible. Okay, go for it, Giacomo.
Good question, though. Okay, so this is one example. This is what we look at first. We just take the approximate wave function that describes the A plus state, and we essentially fiddle with the squeezings in these wave functions, and we'll look what those how those affect the fidelity with respect to the plus state, which is the state that we want to encode. Now, what I mean when I say approximate GKP code word is here below in the asterisk. So it's essentially what I described earlier. We convolve an ideal code word with a Gaussian, and then we apply an envelope to normalize it. Here I'm looking at, well, when I say squeezing parameter, I know it's not exact, but essentially what I mean is it's one single parameter that controls the width of the overall envelope and the single peak's width. So keep that in mind. When I talk about squeezing, I'm talking about how good an approximate wave function is. So if you look down below at excellent, for example, you see a wave function that has a very wide envelope. That is, there's a lot of peaks. That's a good wave function. How do we know it's good? Because we can look at the block vector, and the block vector is exactly a plus logical state. Good. What happens when we fiddle with the envelope parameter? We get this good wave function that is the point B. So it points the state, the block state points toward the center of the block sphere. And then we can just increasingly damage our code word until we get a bad code word and we get a terrible code word, which is a zero logical. That is, what we want to encode is a plus state, but what we end up with, if it's squeezed too much, is a zero state. So it's not the maximally mixed state, it's a zero logical. Keep this in mind. Now, the formalism is is flexible enough, so we don't have to just look at one state at a time. This is a funkier example, I guess, of just tracking different states in the block sphere. Here on the right, we get, it's the same idea as the previous plot, just with more states, and each orbit here is a different value of the squeezing parameter. Another thing that I think is important to point out is that we can, if we want, just literally write down the logical density matrix for these states. So the purpose of this is not that I want you to look at the thing on the right and think, oh yeah, that's obviously a plot of the thing on the left for different parameters. I just want to showcase a little bit. I just want to show you what can be done. And we could, just in principle, write down the density matrix. This is an example of how it's been used in other literature. For example, here we see they're investigating the logical subsystem, the logical properties of a different type of approximate code word. That is a code word that is built by acting with this E of epsilon operator on an ideal state. So it's a different type of approximate code word. This is another paper that uses the formalism, and essentially they use it because they just want to benchmark their own decoder. And what better way to do it than only isolate the logical information and give the result in terms of fidelity. So that's another way to use it. Here is a relatively comprehensive study of how different states behave with respect to this, the logical fidelity of different states behave with respect to squeezing. This will be the serious version of the 3D plot that I showed you earlier. I just want to underline two things. The top three squeezings are 12 dB, 10 dB, and 8 dB. And we see one type of behavior, if you will. If you see there's a theta equals pi on 2 region where the fidelities are much lower than the fidelities for theta equals 0. This in the block sphere would be geometrically the plane perpendicular to the 0, 1 axis, to the computational basis axis. So for high squeezing, we have that the worst type of state lies in that plane. For lower squeezing, that is 6 dB, 4 dB, 2 dB, it shouldn't matter really because these states are very bad. They have very bad squeezing. But I just wanted to point out that the behavior is different. So there's two regimes, the high squeezing regime and the low squeezing regime. And the low squeezing regime is very bad, and I don't think it's ever gonna be useful for actual quantum computing because of the fidelities that come out of it, essentially. Now, I also want to talk about an application as a whole that is continuous variable cluster states. This is, in this example, I'm not looking at a state and telling you what the fidelity is. Here, what I'm doing is I'm looking at a computational scheme as a whole and see if this decomposition can somehow fit with it. I want to see if this decomposition can actually tell us more about this computational scheme and the reason why it works. So there's not much to that you need to know about this, but the important things are these three things. Number one is that qubit cluster states are a resource for fault-tolerant universal quantum computation in a measurement scheme. Number two, and this, I'm talking about qubit cluster states, no CV, just normal qubit. The same is true for CV if we use GKP states as our carriers of information. And the same is also true for CV cluster state, but that's a different type of universality that I don't want to talk about, and I don't think is very practical. When I talk about using CV to achieve fault-tolerant quantum computing, what I mean is that we want to use the CV cluster state as resources, and these resources enable us to perform operations on GKP states.
Giacomo, you've got 5 minutes.
Now, in these 5 minutes, I'm just gonna do I'm just gonna tell you what the main results are. Now, if we want to implement a gate with cluster states, this is what we do. We take our middle part, which is the computational resource, which is zero momentum eigenstates connected by a generalized CZ operation, and the data qubits. What we do is we keep measuring. We can measure the nodes, we can measure the data, and what we end up with by, if we keep measuring well pre-selected nodes, is we end up with this. We end up with a control operation on the 2 data qubits and a bunch of unitaries that multiply these. Now, if we fiddle with the measurement bases that we had chosen previously, we can take these this total operation to be a general unitary, a 2-mode unitary that we want to implement. So we can to sum it up, we take this resource, we do a bunch of measurements with respect to pre-selected bases, and what we end up with is that we can do any 2-qubit unitary. Now, what happens if we use this decomposition on a on these nodes, on these black nodes that constitute the fundamental unit of a cluster state? Well, this is what happens. The subsystem kind of split a little bit like an accordion, and we can see that there is a complex interaction. There is complicated interaction between the top blue diamonds, which represent the logical subsystem, and the rest of the diagram, which represents the gauge subsystem. What does this mean? What does it mean that our logical subsystem, which looks a lot like a discrete variable cluster state, in fact, it is a discrete variable cluster state, what does it mean for this part of the diagram to be entangled with this gauge mode? Well, it means that the information is not readily available. It means decoherence. Entanglement means decoherence. Turns out that by connecting a GKP state, we are simplifying the entanglement structure of these states to the extent that if we only use GKP states, what we end up with is literally a discrete variable cluster state completely decoupled from the rest of the subsystem, which is nice. We can also give the same treatment to proximate nodes. And by the same treatment, I mean just this, looking at what the logical information hidden within the state is. And I don't think I can go through the whole thing in 1 minute, 10 seconds, but essentially, I'll give you the flavor. We start with a state. We start with these single nodes, and we decompose them. Well, what happens when we decompose them is that new entangling operations kind of appear within one single node. So the node itself is decohered. We can now plot stuff like how much squeezing we need for our state to have 0.99 fidelity. And we can also analyze more complicated schemes, such as the double teleportation scheme, which is a staple of continuous variable cluster states. This is the basic mechanism of CB cluster states. And we can, for example, you don't need to worry about this too much. But what we can see here is that we can, for example, do this teleportation protocol on any state. Here is it 0 GKP or plus GKP, but it doesn't really matter. And we can look at it after the protocol and plot stuff like the logical infidelity of the state, so as to gain insight on which states are more resilient in the context of a broader computational scheme, instead of just writing down a wave function and saying, okay, let's look at the logical fidelity of this wave function. So yeah, in conclusion, I just want to point out that this is a heavily GKP inspired and GKP compatible way to split, to give a change of basis in order to write any continuous variable state as a logical carrier, or as a carrier of logical information, which is what we care about when we want to think about quantum computing. And the rest is kind of factored out, and we don't really care about it. It's a gauge mode, and we may have some degree of freedom with that. Yeah, with that, I thank you for listening, and